Okay, we're theoretically live, but as usual, whenever I go live here on YouTube, I require some kind of external confirmation, some kind of acknowledgement of my existence. Am I real? Are you real? Is this all just a dream? Are we a brain in a jar? Who can say? Okay, there we go. People said that they see audio and video, so I can confirm that this exists. So, first, if you've never watched the live streams that I do, or you've ever even kind of noticed that these things are happening, that's because we have historically been making them unlisted after we complete the live stream. But things are kind of changing. And so there was a couple of reasons why we used to do that. So one is that YouTube's algorithm penalized your channel at a sort of large scale way. And if you had longer videos, then, and people would not necessarily watch the entire longer video, then you would get some kind of sort of demotion of your entire channel. And so if you want to kind of keep the channel doing well, people would even go and like delete videos that were underperforming to try and bring the watch statistics up to the point that it made YouTube happy. And YouTube has gotten a lot better about this. And in fact, it sort of rewards longer videos. And we find that some of the longer videos that we do, they have a longer watch time. And so we see, like, whenever we would accidentally leave these live streams listed, they actually get a lot of views. And so we're going to try an experiment, which is that we're not going to unlist it. So I can't guarantee that this is what's going to happen. Like if we see our whole channels go down, then we will sort of go back to the way things were. But if this works well and people enjoy this. Now, keep in mind that now you're going to be getting some repetition, right? You're going to be getting the stuff that is, oh, I should be recording. Chat's going to kill me. So keep in mind that this stuff is repetition. So at the end of the, like once we complete the question show, this thing we do every Monday, then Chad and Anton, our editors, hack this thing up and turn it into the question shows. And it lags. So you'll watch this live stream on Monday or shortly thereafter, and then we will go live with the question show the week after that, which will be made up of that. And then some of the bits and pieces of this will show up later on. And so if you want the version that has the nice graphics and the music and my longer rants at the end, then you may want to just skip this and wait, and all of the material will make its way out eventually. But if you just can't wait and you want to, watch it as soon as it happened, or I don't know, if you like second screen it and you're just like working on some project and you want to hear Fraser talking in the background to keep your mind distracted from the just existential horror of existence, then just keep watching. I think this will work really well. But for those of you who are watching this live and you know who you are, then this is your chance to hit me with your questions. And I will spend the next 2 hours answering your questions about space and or astronomy. Zephyn's here, which is good, which means that we got a little moderation happening. That'll help pulling questions over into the database. Okay, so a few ground rules. So the first ground rule is just, I try to give emphasis to the people who've never had a question answered before. So if this is your first time, I like your chances. The second thing is just to remember that I am a journalist, not a scientist. And so if you want to get my opinion on some esoteric theory about something, I cannot provide you an opinion. I can only provide you the scientific establishment mainstream consensus. And for some of you, that is fighting words. That is me saying that I'm a sheep, and all I do is say what the scientists tell me to say. And you're absolutely right, because I am not a scientist. They are. And so I do not have the scientific capability, the experience, the education to be able to have original theories about concepts in space and astronomy. My job, my expertise, my specialization is to be able to communicate what they know to you. And then the last thing is, we get a lot of the same questions over and over again here on the channel. And on the one hand, I love to just hone my answers time after time after time. But also I know that the audience gets a little tired of hearing the same question. So if I don't get to your question, it's not personal. It might be that we've just answered that question. What do you think about UFOs? What is the universe expanding into? What came before the Big Bang? Those kinds of questions. It might be that we just have answered that question a lot. Now, Lagrange point questions are always welcome. And of course, now the solar gravitational lens, which is the new Lagrange point, is also always welcome. All right. So I think I've got a chance to sort of catch everything up. So before we get into your questions, which you're watching before the people who are watching this live get a chance to put your questions in, or I start reading those questions, I'm going to grab one from the YouTube comments. So, Dwayne Sapling 9468. What's up with all the thumbnails with the content creators exhibiting affected looks of amazement and consternation? Et tu, Brute? Yeah, so this is one of the things that you see on YouTube like crazy. You'll get a shocked soy face. Is that what it's called? An amazed face of the person who is in the video. And you'll sometimes have like a little arrow that's pointing something on the thumbnail. And you're like, you won't believe what this is. And then there'll be a title of the video. And then there'll be some text on the thumbnail. And the whole thing is just designed to reach into your lizard brain and increase the chances that you're going to watch this video. And so why do people do this? Because it works. Because having a human face who is expressing some kind of emotion in a picture is something human beings are just drawn to. And so that alone will get a person to your brain is like looking for eyeballs in pictures around. And so that sort of triggers your brain. And then there's going to be other information on the thumbnail that's going to have you go, there is a question here that I need to know the answer to. You won't believe what happens next. These are all the tools that people use to try to get you to watch their video. Now, if you do not deliver on the promise of the thumbnail and the title and the description, then that's clickbait, right? Then you are essentially bait and switching people to come in and watch your video. But if you deliver on the things that you are posing in the thumbnail, and if it is indeed you, look at all the AI slop videos where it's Michio Kaku going, oh, I can't believe we've been lying to the public for so long, right? That's all AI slop, and the videos don't deliver that unless they are actually deep faking Michio Kaku, and he should sue them. But I'm actually in these videos. I'm on the thumbnail and then I'm in the videos. And specifically, we do it with Space Bites. We don't actually do it with the rest of the videos. And that's just to give you a kind of visual clue to know that this is a Space Bites episode, because it's me on the thumbnail making some stupid, whatever horrible frame that Anton has captured and put into the thumbnail. That's the one that you see, and that's me. So it's the game, man. Hate the player. No, wait. Don't hate the player, hate the game. That's it. Don't hate the player, hate the game. And that is because YouTube is a dog-eat-dog battlefield where people are pitted against each other for the enjoyment of the YouTube executives to see who can survive and who will wash out. And so the way you try to increase your engagement, try to turn this into a career, is you try to be present and you use the kinds of techniques that work. And I could absolutely not do those kinds of thumbnails. Very bland, very boring thumbnails, like the way I used to. And I would get 1,000 people watching my videos as opposed to 50,000. So I think, for people who this bothers, and there's a bunch of you out there that this really bothers you and it just gets under your skin and you hate it, right? Which is just like, who do you want to survive, right? Because it is an absolute knockdown fight, drag out fight right now between human beings who are trying to produce content and the robots. And So we have to, and the robots have no shame, and the people who run the robots have no shame. And we have to do what we can to still have a little bit of shame, but also be able to try to compete and try to get more scientific awareness out there, try to connect with the public, try to deliver on the promises that are put on our thumbnails. And so, you know, if it were up to me, I would not have my stupid face on the thumbnails in the poses that Anton chooses. But Anton is the expert, and he knows what's going to work to get people to be able to go and check out the video for more. So that's why we do it. It's what everybody does, and it is very effective, and it helps make your channel grow. And if you make your channel grow, then you reach more audience, you educate more people about space and astronomy. Anton's in the chat right now. They are not horrible frames. They are great frames. All right, Anton. Well, maybe, you know, I'm the one who has to look at my face where you have grabbed frames from me making derpy faces, and I just have to tough my way through it. And I do. So, you know, I never whine about it, but I notice every time. All right, let's get into the rest of the questions. Jack C. Branch. Hey, Fraser, given the danger from radiation, being in space combined with the vast distances, isn't it unlikely that any aliens would survive the journey to Earth? So traveling in space is extremely dangerous. And the radiation alone is something that you looked at. And, you know, if you're outside of the magnetosphere of the Earth, you're experiencing hundreds of times as much radiation from cosmic rays than what you would experience just down on the surface of the Earth. Like, it's bad. And like, feel you full of cancer after a few years of traveling in space, bad. And that's just one issue, not to mention the long times it would take to be able to travel from star to star, the lack of resources that are available to you, the radiation that you're probably going to be producing from whatever propellant, you know, the amount of radiation you're going to be producing from whatever propulsion system that you're operating. Like, these are all definitely big challenges for traveling from world to world. And, you know, it doesn't seem surprising to me that you would be skeptical that like actual physical aliens in their biological bodies would attempt the journey to go from star to star. Like, unless they had warp drives and could do this instantaneously, or walk through a Stargate where you're just like going for a walk around the park, but you happen to be on another planet when you come out the other side, and they all look like British Columbia. You don't go, right? There's no way you would want to make that kind of a travel. What if it took you 1,000 years to go to some other star system? Why would you leave the comfort of your own star system to make that kind of a journey just to drop in and visit, right? You wouldn't. But what about the robots, right? The robots love to go to space. The robots don't care about radiation. They don't care about long duration times. I mean, sure, they'll care a little bit about the radiation as the cosmic rays are wiping out their memory and causing problems in their electronics. But really, like the robots are hardened to space. And so, you know, often the question that we should be wondering is not where are the aliens, like with their bodies? Why are they not here physically, little grays? But where are their robots? Where are the von Neumann probes? The self-replicating robot probes that can go from star system to star system, make copies of themselves, go to other star systems. Like, I would expect the von Neumann probes, I would never expect to see the aliens physically actually making the journey from star to star. Oh, great. Anton is working on a thumbnail for this week's Q&A as we speak. You're just waiting to grab the derpiest freeze frame from me. Church discography. What would happen if a gamma ray burst slammed into a black hole? The black hole would absorb all of the energy from the gamma ray burst. So like, a gamma ray burst is kind of the birth of a new black hole anyway. There's two kinds of gamma ray bursts. There's the short gamma ray bursts that last less than 2 seconds. Those are probably caused by colliding neutron stars. And then there's long gamma ray bursts, which are caused by the death of a massive star, something that is like really big, dozens, if not more than 100 times the mass of the sun. Thing collapses, you get a black hole at the center of it. And then you get this sort of radiation that comes out, like a supernova, but you also get these collimated jets of material that come out of the poles of the object as it is forming this black hole. And we know that even if one of these things is, hits the Earth from halfway across the Milky Way, it can cause severe damage to the atmosphere, wipe out a lot of the ozone in the atmosphere, make us more, so let more of the radiation from space make its way into the planet, or through the atmosphere and cause damage to life on Earth. So they're really bad, but black holes can feast on energy, no problem. And so you would imagine, let's imagine like the perfect scenario. You've got this gamma ray burst, star collapses, blasts out this collimated jet, the collimated jet blasts, and a black hole happens to be perfectly in the path of that gamma ray burst. Well, the spread of the gamma ray burst is going to go, much wider than the event horizon around the black hole. Over the, they have an angle of like 5 degrees. So imagine the sort of 5-degree angle coming off the gamma ray burst as it's sort of going out into space. So by the time you are several light years away, it's very big, while the event horizon of, say, a stellar mass black hole is going to be, well within the orbit of Mercury. So they're very small. But some of the photons, the gamma rays, coming from the gamma ray burst are going to hit the event horizon of the black hole. And they're just going to go right in, and they're going to add to the mass of the black hole using E = mc squared. You just calculate the energy of the photons. That will help you calculate the amount of mass that the black hole absorbs, the equivalent amount of mass. And the black hole will get a little bit bigger. Its event horizon will get a little bit bigger, get a little more massive, and then it'll be a bigger target for future gamma ray bursts. So no, black holes can totally handle gamma ray bursts. Yum, yum. Hello from China. How cool is that? How? Lubo, how are you watching us in China? Are you on a VPN or something? I was just interviewed on CGTV, the US. So I guess I was interviewed on Chinese television, but in the United States. I wonder if that plays back in China at all. Neil Von Holtum. How much longer do we have to wait until AI explains how to make a warp drive? You could probably get an AI to explain how to make a warp drive right now today. If you spend enough time stewing in its sycophancy and hallucinations, you can probably get the AI to start telling you that your ideas about a warp drive are 100% rock solid. And all you need to do now today is just build a prototype. And I get probably an email a week now, maybe less, maybe an email every 2 weeks from somebody who is telling me that they have developed an idea for a warp drive because of their working with an AI, with ChatGPT, and all they need to do now is build a prototype. Well, the build the prototype part is the part that matters, that no amount of sort of thinking about an idea about folding space-time and hashing it out with ChatGPT is going to get you to an actual working warp drive. You actually have to build the thing. And then right away, you will find out all of the flaws and the shortcomings of how the system works. But, the question you're asking is how long until it actually can help us make a working warp drive? And I've said many times in the past that the fact that we don't see any alien civilizations with working warp drives today tells us that we will probably never be able to build a warp drive. But, who knows? Maybe there is a design for a warp drive, or we're alone in the universe and then we're free to build warp drives. So you're going to need a lot of stuff happen where the AIs can actually innovate. They can actually come up with ideas, engineering ideas, scientific concepts, come up with ideas that extend beyond the existing just the repository of knowledge that humanity has gathered together. And the AIs can't quite do that yet. They can take ideas that have been explored really well in sort of one area, and then they can extend that across, or they can apply tools to turn something that, someone just hasn't gone through the entire search space to figure out yet. They can go through that search space and come up with novel solutions to, mathematical challenges and things like that. But, to actually physically build a prototype, we are quite a ways away from just that kind of stuff in general. And then specifically building things that could very well be impossible, that's going to be a couple of years after that. So I'm going to say, I'd say I want to joke about this, but I mean, the technology is changing so rapidly that I do feel like we are all that sort of frog in the hot water pot, although that analogy is both awful and apparently incorrect, but that we passed the Turing test. And nobody really cared. Like, you remember when we used to think, oh, it'd be crazy when some kind of technology, when AI passes the Turing test. And here we are today, and the AIs absolutely passed the Turing test. If you don't know, you would know that you're talking to an AI, or the average person would know they're talking to an AI. And so the technology is advancing, and the technology is starting to be used to make the technology better, and it has this flywheel. So who knows? I think we're probably 5 years away from AI being able to be innovative and making scientific concepts that have never been seen before. But then actually turn those into physical things, maybe that's like 5 years after that. And then to make a warp drive, 5 years after that. So, maybe 15 years away. ABC Boat 2XY. Realistically, based on your experience and knowledge, when do you think we will get humans back to the moon? So, I mean, at the time that we're recording this, at the time that you're watching this, the Artemis 2 mission is either going to launch almost tomorrow, or we'll have to wait because it's scrubbed a bunch of times and we'll have to wait another month. But we're going to have humans get on top of the Space Launch System, and they're going to fly around the moon in a week. So soon. But obviously, I think what you're looking at is, when will humans set foot on the surface of the moon? And that is going to take a little longer. Right now, the Artemis 3 mission is scheduled for probably 2027, 2028. But even then, there's a bunch of issues with the lander. We haven't seen Starship do a bunch of the things that are required to demonstrate that it can be the lander for the Artemis 3 mission. Maybe they'll sort those out, but if they don't, Blue Origin has its version of a lunar lander. So someone will figure that out probably by 2030. And at the same time, the Chinese are planning to send humans to the moon by 2030. And so far, they've hit all of their milestones. All of the missions leading up to their human missions to the moon, all of the Chang'e missions, their Mars missions, sample return missions, these have all come together. So it would not surprise me if they just hit their timeline. Their space station, they're servicing to and from the space station. This is all happening. So it really feels like 2030 is the date when this will probably happen. That NASA may have a few more delays, but be really trying to race to get everything to beat the Chinese back to the moon. And the Chinese are going to follow their schedule, and I think you'll see someone set foot on the moon in 2030 at the latest and maybe the earliest. Jasper Rost. Is it possible that a form of life completely unrelated to known Earth life could exist deep underground? I mean, theoretically, yes, but the chances of it being completely unrelated to life on Earth is pretty low. There are some who think that the bulk of the life on Earth is actually underground, that we have extremophile bacteria that can handle temperatures of up to like 130 Celsius. And so, if you do the math, life is probably sustainable all the way down to about 6 kilometers deep underground, at which point temperatures get to about 150 Celsius. And then below that, just nothing can survive. But there's water mixed in with the rock down to those depths. And when you sort of consider the surface of the Earth, you consider this shell of the Earth 6 kilometers deep, that's a lot of room for life compared to what's on the surface. But water gets from underground to the surface, from the surface to underground. And so we're connected to all of this life that's underground. The idea that I like that's kind of similar is this idea of shadow life. So, all life on Earth shares a common ancestor. At some point, 4.1 billion years ago, something went from, some combination of hydrocarbons and basic sugars and alcohols and electricity and other chemicals, and who knows how it worked. We went to something that could be the first life form, something that was self-replicating, something that could, where Darwinian evolution could take over, and then it could evolve into the other kinds of forms of life that we have. Everything, every single life form that has ever been found on all of planet Earth can be traced back to that same ancestor. But maybe, if you had one abiogenesis, you had one thing that went from non-life to life, maybe that's happened multiple times. Now, if it has happened multiple times, then maybe all of the times it just got eaten by something, more well established. If you've got a dinosaur and then, I'm trying to think, but if you have like some little blob of chemicals turn into something that's like maybe a little bit viable, and then a dinosaur walks along and slurps it up, and that's that, right? But what if some other kind of life formed and it is incompatible with life as we know it? And so life on Earth wouldn't perceive it as food. And it would, in fact, the kinds of tools that we use to perceive life in general are really reliant on the kinds of chemicals, the kinds of processes that, DNA, RNA based life goes through. And so there could be an entire shadow ecosystem here on the Earth that has been with us forever, doing its own thing, that we have just never known. Now, it has to be bacteria-sized in nature. Like if there were shadow trees, I think we would spot them. Shadow dogs, right? But bacteria deep underground that uses its own chemistry, its own sources of fuel, completely unrelated from the life that we have, it would actually be really hard for us to find out. And so this is an idea that biologists consider is shadow life. And so, people talk about this idea of like making life mirror life, right? And so you just like take the chirality of DNA and you flip it around, and it's probably viable and probably very dangerous. But that's like the kind of thing, but even like more exotic than that. We could have aliens here on Earth, but they're not really aliens because they evolved here on our planet as well, and they have as much right to this planet as we do. Mark Vonstein, started the show. You said you won't give your opinion, but you have given an opinion multiple times about America being unfair to Canada or other countries, which is very much an opinion. Sure. Yeah. I'll give you an opinion about what it's like to be a Canadian. I know what it's like to be a Canadian. I just don't give you astronomical opinions, scientific opinions about things that I am I do not have the educational experience. But the one thing I can definitely bring to the table is what it's like to be a Canadian who's married to an American. So I have even more experience. Lubo in China. What is your favorite telescope? So I've got a bunch of telescopes now. Man, like this is like space nerd problem, which is that I've been getting a bunch of demo units. So I now have 5 telescopes, which is a lot. So I have the Dobsonian, the 8-inch Dobsonian that I bought with my own money. I have the C-Star, the S50, which I bought with my own money. And then I have the Vespera from Vaonis, which was sent to me as a demo unit. And then I have I don't know if you can see it, but I have an 80 millimeter refractor up there. And then I just got a Dwarf Mini sent to me as a demo. And this is really cool. I've only had a chance to like take one picture before the cloud sucked in, and then that was that. So I'm looking forward to another clear spot. You can tell we've got clouds because all the telescopes are back here in the studio with me. So what is my favorite telescope? Well, my favorite telescope is the telescope that I had when I was 13 years old. I had a 4-inch Newtonian reflector that I bought from a company in Vancouver. Riverside? Oh, I forget what it was. And it was on an alt azimuth mount, so it wasn't on a equatorial mount. You had to sort of, if you want to look at something, you had to be able to get good at zigzagging with it. And I had bought it because there was like a garage sale on where I grew up, and I picked up, someone was giving away literally hundreds of astronomy magazines and sky and telescope magazines. And so I had all of these magazines sitting in my room, and I would just go through them page after page, reading the stories, looking at what was up. And they were from 10, in some cases fairly new, others cases 15, 20 years back. And then they all had these ads for telescopes. And so I really got to know the different kinds of telescopes that were out there. And then I decided I'm buying a telescope. And then I did a lot of research, and I found a company in Vancouver that was relatively close to me, and I bought the telescope. And did I pick it up? I think I picked it up, brought it back home and set it up, and it blew my mind. Like, I saw Saturn through a telescope for the first time. I saw Jupiter. I saw Mars. I saw the ice caps on Mars. I saw the bands across the planet on Jupiter. And then I began to learn the night sky, learn the constellations, and it was incredible. I still now today, I walk outside, the constellations in the sky are this map that I understand, that I learned when I was 14 years old, and it's never gone. It's never left me. So like, if you haven't learned your constellations, learn your constellations. A pair of binoculars are the best way to do this. You can see a lot of the bright stuff in the constellations right now. Andromeda Galaxy, Orion Nebula, various clusters, the globular cluster in Hercules. You can see the planets. Like, they're great. Binoculars are great. But yeah, so that was my favorite telescope. And this is so much of a better telescope, right? Like, an 8-inch Dobsonian beats a 4-inch Newtonian, hands down. Even an 80 millimeter refractor beats it. But in my mind, when I look back and I think about what it was like to look at Saturn, look at Jupiter through that telescope, it's better than this, which it's not, but it feels like it was. So yeah, it's my nostalgia telescope is my favorite telescope of the group that I have behind me right now. I would say my favorite is not here, which is my astronomical binoculars. So the binoculars are number 1. And then I would say it's the Dob and the C-Star are sort of 1 and 2, and they flip back and forth. Like, if I want to look at something visually, you go with the Dob. If I want to take a picture, you use the C-Star. But yeah, the nostalgia scope is my favorite. Tubiel. Fraser, I wonder, have you, to your knowledge, inspired scientists during interviews to pursue a certain new idea because of you? I find it interesting. Haven't thought of that. Nope. No scientist has ever written back to me and said, hey, Fraser, based on that idea that we talked about in our interview. I looked into it and now I'm writing a paper about it. Thank you so much. Do you want to be a collaborator on the paper? No, that has not happened. If anyone ever wants to do that, I would love it, but no. And although in the moment, you know, it feels like, oh yeah, I just suggested something to them that's totally innovative and they hadn't even thought of that. And, you know, this is going to be groundbreaking. That's just my lack of knowledge talking, right? That it may be an interesting idea, but has been, once you do literature search, the idea has already been done and checked. And there are people who know this information better than the person that I happen to be talking to. So no. And it wouldn't even occur to me that someone would ever take one of my thoughts and turn it into an actual like science paper. And you know, partly it's not like maybe it is something that's relatively new and it hadn't occurred to them, and maybe there is a paper in that. I don't know, but it's a lot of work. Like the hard part of doing a paper is not coming up with the idea or the interesting question or the I wonder. It's doing the hard work of making the observations, putting the pieces together, doing the literature search, crunching all the data, putting it out for peer review. Like that's the work, and you kind of want to do the things that have occurred to you. So no, it has never happened. But he does have an asteroid named after him. Yeah, I have an asteroid named after me. Sorry, just looking through the questions. Jimmy James, were you ever on local dial-up chat like STS or D-dial? So, I mean, I used to use bulletin boards when I was younger, but the problem was I grew up on this island and we had terrible telephone service, and we had a party line. So I don't know if any of you have ever experienced a party. The old people have experienced a party line. And so you share the phone line with all of the houses in your neighborhood. And so you would pick up the phone and then you would hear somebody talking on the phone. You go, oh, sorry about that. And then you put the phone back down because some other house had the phone at that point, had the line going. And then it wasn't until I was probably 10 or so that we actually had our own phone number and our own phone line, and we weren't on the party line. But then there were no bulletin boards that I could dial into that were relatively close. But I was living in Vancouver and I was doing some bulletin board service, but then it's always the problem where your mom says, get off the phone. I need to make a phone call. You know, they pick up the phone. It makes all these modem-y noise. Young people, you have no idea what you missed out on for that. I think my first modem was like a 2400 baud modem. But there was some great, you know, again, nostalgia, right? You think back to the original Usenet and the original conversations that were there. It was so pure. I remember like the first jerk who posted onto Usenet spammed something about immigration or something like that across all the Usenet news groups. And it like everybody lost their mind because all of their precious discussion forums had now been corrupted by somebody posting multiple times. But yeah, so I definitely used like modems and dial-up and all that back in the day. Just Chris, if we were able to be stationary in space, would we be able to see the movement of stars, planets, etc.? So everything is relative in space. So right now you are standing on the Earth and the Earth is going 30 kilometers per second around the sun. We see the sun move, but actually we're seeing the Earth rotate. But we can see asteroids, comets, we can see the other planets move from perspective of the background stars night after night after night. We see the moon move night after night after night, right? Because they are moving with respect to us. And if we went to the moon, then we would see different things moving. And if we were on the sun, which I do not recommend, then you would see different things moving. And so there is, like one of the key concepts of astronomy, cosmology, or really physics, is that there is no sort of default reference frame. There's no one place that is like, this is the place where you then watch everything happen, and this is the right place. There is no right place. Wherever you go, everything is relative. And so it's just, where do you want to put yourself at what velocity to see what you're going to see. There are times when asteroids come very close to the Earth, that you can, like when Apophis, which is this asteroid that's going to come close to the Earth in whatever, 5 years or so, you'll be able to see with your eyes, and you will literally be able to watch this dot move through the sky, like the way you can watch a satellite move through the sky. So, but otherwise things are just moving so slowly. In Cudmore, Fraser, in your opinion, what is the best Lagrange point to report news stories on? I don't even understand the question, because they're all so great, and I will report on any Lagrange point. So, like, which one is easiest to explain? They're all kind of difficult to explain, whether they're the stable ones, the L4 and L5, or whether the unstable ones, L1, L2, and L3. What are the good reasons that you would put things at the L1 point, if you want to be able to observe the sun, or if you want to be able to observe the Earth from a specific location, or you want to go to L2 if you want to be on the other side of the Earth, so that you can put the Earth, the sun, and the moon all in the same spot in the sky, and then shield them, and then you can look out into space. Or you can use L2 as a jumping off point to go out into the rest of the solar system. So, man, I don't have any favorites when it comes to Lagrange points. Although I do kind of like the L4, L5 Earth Moon Lagrange points, but mostly because that's where we'll put our giant rotating colonies once we finally understand that gravity wells are for suckers. Then we want to live in space. So those would probably be my favorites. Samurai says, what Lagrange point would you like to report from? Yeah, so L4, obviously. I want to be there when the O'Neill colony is built at Earth Moon L4. That would be amazing. Yes, please. Luke Skywalker. My daughter asks how black holes are made. Okay. All right. So I don't know how old your daughter is, but I'm going to assume that she has an intellect that scales beyond anything we can scarcely imagine. So she can handle what I'm going to be spinning. So when you have a massive, like all stars, like why are stars, right? And they're stars because they are in this balance. So you've got gravity that is pulling the star in on itself, wants to collapse that star into itself. But then you also have the light pressure pushing against the inward pull. And this is amazing, right? Like at the center of stars, they are mashing hydrogen into helium. They are making heavier elements. And as they do that, it produces gamma radiation. And that gamma radiation, these photons that are bouncing around inside the star, push out against the star, stop it from collapsing in on itself. As a star, like a big star, gets older, it uses up all of the hydrogen in its core, and then it switches to turning helium into heavier elements. It can turn things into carbon and oxygen and neon, and it just keeps making heavier and heavier elements in its core. All the while, it is producing this gamma radiation that is pushing against the gravity that's pulling the star in. And it gets all the way up to iron. And iron is this very special element that when you make iron, you don't get the gamma radiation in the way that you did with all of the other elements before that. And so now there is no radiation that is blasting out of the center of the star in the same way that it was there before. And now there is nothing holding all of that gravity that was keeping that entire star out. It all just collapses in on itself, implodes. And it can go like 70% the speed of light as all this material is falling inward. And you get this black hole forming at the center of the star because it's just being compressed down, where you've got all of the mass of this star just collapsing in on itself. And that's how you get a black hole. You have to tell me whether you understood that. If not, ask follow-up questions. Okay. Heavy Kev, have you ever seen the stars from New Zealand? It's awesome viewing down there. I have not. The closest is I've seen the stars from Australia, on the east coast of Australia. And it was incredible. Like, the best stars I've ever seen were in Australia. We weren't in the desert, in the outback, but we were away from the cities on the east coast. And like, there's a bunch of things. One is like, it was just, the sky was so dark and the stars were so bright. But the other thing is just that the Milky Way was directly overhead from our perspective. And so the densest part of the sky, where the most stars are, was right overhead, the clearest part of the sky. And so it was just incredible. I still, like, you know, when was I there? 2019, I think. And it was stunning. So yeah. So I'm sure New Zealand is amazing too. Just, you know, it's the opposite of what we experience here in the Northern Hemisphere. So the constellations are unfamiliar, which is also very cool. Cortos, are there any NIAC programs that have made progress since your last round of interviews? It's about time for the next announced group of NIAC awards. So generally what happens is they give out about 12 round one NIAC awards at the beginning of the year. And then they give out maybe 4 to 6 round two awards partway through the year. And then they'll give out the occasional round 3 award, and they kind of happen randomly. So we're going to have to wait. We're going to see an entirely new crop of NIAC awards probably within a couple of months. And then later on towards the summer, we'll see that round 2 where we find out the earlier ones that have been funded even deeper. So I haven't heard anything new. You know, I promise you, the moment there are more NIAC awards, I reach out to every single researcher and say, can I interview you, please? And I get most of them. So that's awesome. Vista Tutti saying, Aussie skies are awesome. We are blessed. New Zealand has mountains, so I hear even better. So, like, where I am in Canada, we have mountains, and that definitely takes away from the viewing the sky experience. Like, I think maybe what made it so impressive for me in Australia was that it was close to the horizon. The sky came right down to the horizon in all directions. And so it really felt like a dome instead of this patch sort of bookended by mountains, which is my experience here where I live. Ash D. While we're on the Lagrange points, would a binary star system have a different set of Lagrange points? So the key to having Lagrange points is that you need to have two masses that are dramatically different by several orders of magnitude. So I think it's 50 times. So the bigger thing has to be 50 times more massive than the smaller thing, and probably even more than that. And so the 30, anyway, you need, to get a Lagrange point, you need to have one object that is very massive and then an object that is a fraction of that mass that is orbiting around it. And that gives you the Lagrange points, which are these stable places. And so if you have two binary stars that are orbiting around each other, you don't have that disparity in their masses. Now, binary stars can behave like a single massive object once you are sufficiently far enough away from them. So, if you've got two stars, they're orbiting around each other. When you're really close, then the gravity is this tangled mess that if you get too close, you're just going to go into one of these stars. But if you get far enough away, like 2 to 4 times the distance, the separation of the stars, you can orbit around them stably. That, a planet can orbit around. It's called circumbinary planet. And so it can orbit around both stars of the binary system in this stable way. And then the Lagrange points are back in play, although they probably get a little weird just because, the two stars are orbiting around each other. So it's not exactly a perfect, point of mass. But if you get farther enough away, then the Lagrange points will come back into play. No username. Wait, if life can survive at such high temperatures, then why is 60 degrees plus considered the cutoff? I remember a paper where hot ocean worlds were considered unviable. Yeah, like the hottest that life has been found so far is, I think, 130. Pompey worms can handle 130 Celsius, so they can handle hotter than boiling. And I think 150 is the theoretical limit for the most extremophile life. So I'm not sure why 60 is the cutoff in your mind. Arjone, how should the streaming of astronauts during the new moon landing be different from what we landed in the 60s? What cool things should they do now that weren't possible then? I mean, it is pretty amazing that humanity was able to watch the Apollo moon landing live when it happened. I mean, think about the engineering. And there's this great video drama about what it took to be able to get the radio telescope in Australia aligned so it was able to broadcast the Apollo landings while it was happening. And yet, it was before my time, but, my dad remembers it fondly. And I'm sure people who are watching this right now fondly remember being in school and them putting that on the television. And you were watching a person set foot on the moon for the first time in human history. And it happened live. So obviously we have a revolution in technology at this point. We have miniature cameras. We have high definition broadcast. The technology is totally different at this point. And yet, you still have the challenge that being at the moon is much, much farther away. And so you're kind of limited by how much you can live broadcast back to the Earth. If you're hoping that you could try to send 4K, it'd be really tricky to get that kind of throughput from the moon back to Earth in a way that it could then be broadcast live. Now, obviously, there'll be hard drives. They'll be able to store the information. They'll be able to bring it back, and then they'll be able to display it. But for the live feed, I would be shocked and surprised if we got anything. If we got even high def, would be amazing for the live. For all the live stuff that was happening. I think we become really spoiled from SpaceX because they put all these cameras on their spacecraft, and we get a chance to see drones while Starship is lifting off. We see the view from the different fins on the spacecraft. We see the landing drone where the rockets are coming and landing down in the ocean. And so that's the level that we would love to be able to see during these upcoming human moon missions, whether it's from the Americans or from the Chinese. But we didn't see that. Like with Artemis 1, we got some cool pictures, but we didn't get like live video coming from Artemis 1. And I don't think we'll get that from Artemis 2. And we definitely won't get, we'll get some kind of live broadcast for Artemis 3, I'm sure, but it won't be the kind of multi-camera setups that we would all love to be able to see, just because still the bandwidth going to and from the moon is limited. So, but yeah, I can't wait. Arjun, maybe we could use lasers like they did to transmit the image of the cat. Yeah, I mean, so the Psyche mission has demonstrated that you can use lasers as a way to communicate very rapidly from deep space, tens of millions of kilometers away. You're able to transmit it at, broadband levels. And so hopefully they will have some kind of laser transmitter on board that they'll be able to communicate back to Earth and send tons and tons of data back. I hope so. That'd be great. We didn't see that in Artemis 1. And hopefully we'll see. I'll be watching for something like that in Artemis 2. It would be a good time to test that kind of technology, but I haven't heard anything about it. Billions and billions of stars. Any advice on how to spot 3i Atlas through an 8-inch telescope? I mean, there are plenty of websites you can go to that'll tell you the current position of all the comets in the sky. And then, if you have a automated telescope, you just punch in the right ascension and declination number and it will go directly to that object. Otherwise, you have to star hop. If you've got a Dobsonian, you're gonna have to know your sky and know where it is. I don't know what the current magnitude of 3i Atlas is. Let's find out. So was it the Sky Live is a good one. It is currently near Jupiter, which is in Gemini. And what's the magnitude? .8. So that is viewable in an 8-inch Dobsonian. It's a tricky thing to spot it, but you could probably spot it with your eyes if you knew exactly where to look. 8 is sort of a binocular object, and then 10, 12, you need a telescope. Sorry, just looking at the questions. Joshua Butler, is there an estimate on how many dwarf planets there might be in the Kuiper Belt or even in the Oort cloud? No. There are, and I forget the number at this point, 13 planets if you include the dwarf planets. Is there 4? Ceres, Pluto, Eris, Haumea, Makemake, Eris. 6, 7 dwarf planets. And then there's a bunch of objects that are smaller. Sedna, far out, that are several hundred kilometers across. So, for it to be a dwarf planet, it would have to be a lot larger. And so far, none of the surveys have turned them up. So we will have to wait. Now, there are the astronomers that think that there is a Planet 9 out there, that there's something maybe Earth-sized, maybe even Neptune-sized out there that is influencing the objects in the Kuiper Belt with its gravity. Once you get out to the Oort cloud, all bets are off, right? It is so far away. We could have a rogue planet passing through the solar system at like 1,000 astronomical units, and we wouldn't be able to see it. So, we just, to have something that is that close and bright would either be obvious, or it's smaller, fainter, farther away, and is outside the grasp of what we currently have. Obviously, our greatest hope is always on Vera Rubin, which will come online any day now, and it will be scanning that area and will turn up, I'm sure, many, many more objects. But the question is, how many more? Will it find dozens of dwarf planets? Will it find 2 more? We don't know yet. So we'll have to wait and see. Once it starts to find some stuff, then we will get a sense of how much more it could find. Darthex, Oort cloud scares me. Why does the Oort cloud scare you? Werner von Kerman, can a planetary system survive the supernova star, and what happens to the planets if they survive? I mean, you have to describe what you mean by survive. We know that if a star goes supernova within about 25 light years of us, it's a very bad day for the Earth. That the radiation from the supernova will strip away chunks of our ozone layer, will increase the amount of radiation down on the surface of the Earth. If it's even closer, 5, 6, 8 light years away, it'll start to just like tear away at the atmosphere itself. Imagine what it would be like if you were in that system. It would be very, very bad. Like, will your planet get vaporized? Maybe. But you're definitely not going to come back from that. So, and then the star will be gone. So you will be left with either a neutron star, which does radiate, but not very well, or a black hole, which doesn't radiate at all. So no matter what happens, the planets will probably be gone in the explosion. And if they even do survive, then the remnant that is left behind is of no use for life on those worlds. J-Bob, is there something similar to Einstein at Home that allows the general public to donate computing power to help with the Vera Rubin data? No. The way Vera Rubin works is they built this gigantic pipeline, like data pipeline from Chile to the US, the Department of Energy, where they are transmitting all the data that's coming off of Vera Rubin, and then they're processing it to remove reconnaissance satellites, and then they're making it available to the public in pretty much real time. So, they don't need your help. They've got supercomputers, or they've got very powerful computers, huge file servers, but finding stuff, I'll bet you there's going to be a lot of citizen science projects, things where people are crunching through data and they're going to need people's help. So I would just wait. Nothing centralized officially from the people that are running Rubin and, the observatory, but I would wait, and I'll bet you there will be scientists that are looking for help going through the data to find things. Although they might want you for your eyeballs, not for your computer, like at this point, compute is relatively easy to get your hands on. The challenge is the kinds of things that computers aren't super great at, where you actually want human beings. We do this with CosmoQuest, where there have been counting craters on the moon, counting craters on Mars, counting the rocks on Bennu so that OSIRIS-REx could find a landing spot. Something that the computer is not great at. Human beings are able to do that. And so I think that's the kind of work that humans still have a role to play, that citizen scientists have a role to play in, as opposed to just donating computing time. Mr. SM Christian, are there different orbital requirements to put a probe into orbit around Venus as it rotates opposite to Earth? Does the probe have to rotate in the same direction as the planet? No, there's no requirements. You don't have to go in the same direction as the orbit of the planet. The reason most of the satellites are going in the same direction as the rotation of the Earth is that you get a bonus, that the Earth is turning at 1,000 kilometers per hour. And so if you launch in the direction that the Earth is turning, then you can either carry a heavier payload with your existing rocket, or you can use less propellant on your rocket engine. If you want to go the opposite direction, then you have to use more propellant. Or if you want to go in a polar orbit, you have to use more propellant, because you have to essentially cancel out that sideways motion so that you can actually go around the poles of the Earth. So when you go to Venus, it doesn't matter which direction you try to, there will be a most energy efficient way to go into a capture orbit around Venus, and it doesn't necessarily line up with the direction that Venus is turning. And Venus is turning very slowly. So, but no, you can go into orbit in any direction around an object. You just have to use the propellant that's required, the delta V. Casey Ream, how far apart are most binary stars? There's no normal in binary stars. So they're too close where they merge and form one star. But there are examples of binary stars where they're called common envelope, where you've got two stars that are orbiting around each other, and they're so close that gas is coming off of the stars and sort of moving towards the other star. And you have this sort of weird figure eight of what looks like two stars that are starting to commingle. That's how close they can get. And then they can be so far apart. They can be a light year apart in some cases. They can be, when you look at, say, Alpha Centauri, right? That is two stars, sun-like stars that are about 11 astronomical units apart. And then you have Proxima Centauri. I forget the amount. It's, 10,000 astronomical units away. It's really far away. So you can, and yet it's still part of that trinary system. A lot of the stars that we look at in the sky, they look like they're one star, but they're actually a binary system. We can't tell with our eyes. And even with the most powerful telescopes that we have on Earth, it's really hard to pick out the separation between those stars. You need the stars to be lined up in a way where they are changing in their brightness. So for example, they're called eclipsing binaries. So you have two stars that are orbiting around each other, and like transiting exoplanets, when the two stars are side by side, they give off a certain amount of light. When one star is in front of the other star, then they give off a certain amount of light, and so on. But if you have two stars that are orbiting around each other and they're like this, then they're always giving off the same amount of light, and we can't spot the separation between those stars. So we just think there's one star there. And it can take a while, very careful observations, where someone goes, actually, I think that's two stars. That these kinds of discoveries happen all the time. So there is no rhyme or rule to how close or how far apart binary stars can be. Hector Vieira, do all planets rotate? So far that we've seen, they all rotate. The rotation speed can change depending on the planet. I mentioned Earth rotates at 1,000 kilometers per hour. I don't know the rotation speed of all of them. I mean, the day lengths. A day on Mars is about the same length as a day on Earth, so it has a very similar rotation speed, while a day on Venus is like half a year from our perspective. So very slow. Mercury is very similar, very long, very slow day length. I think you can outwalk the sun on Mercury. So it's like less than 6 kilometers an hour. You can stay in shadow while the sun is trying to rise on Mercury. It rotates so slowly. Jupiter takes like just shy of 11 hours to rotate. And so it's rotating so quickly that it's flattened. Like if you look at a picture of Jupiter, you can actually see that it is wider than it is tall. And that is because it is rotating. And Saturn, I think, is even faster. Saturn's like 10 hours to rotate. So they all the planets that we know of rotate, and you would assume that all exoplanets rotate as well. The only way that you're going to get something that is not going to rotate is when it's tidally locked. We have this with the moon. The moon only shows one face to the Earth. Now, the moon does rotate, right? It takes 1 month for it to go all the way around the Earth, or 28 days for it to go around the Earth. And so from its perspective, if you look straight down at the pole, the moon will have completed one full rotation with each orbit. And so you can have planets that are tidally locked to their star. And it's the same thing. Or all of the moons of Jupiter are tidally locked to Jupiter. So they complete one rotation for each orbit. And so is that rotation? It still is, because from the perspective of the stars, you are going through one complete stellar day. So everything kind of rotates. Buzz Lightyear. Any science being done on whether we could ever move the Earth to a different orbit? Like what do you mean by science being done? Like, we kind of know how we would do it if we wanted to, which is that we would do asteroid flybys of the Earth. That if you bring an asteroid really close to the Earth, you do a gravitational assist, you are slowing down the asteroid's orbit, you are speeding up the Earth's orbit a tiny little bit. That causes the Earth to orbit a little higher, a little farther away from the sun. And then 10,000 years later, you bring another asteroid by, do the same thing. You're slowly moving the Earth up higher. And you could just do that so that it is then keeping in lockstep with how much the sun is heating up. And so instead of the sun cooking us in 500 million to a billion years, we could maybe survive all the way out to the very end of the sun's lifetime. And you could be really efficient. So you could have an asteroid that is cycling between Earth and Jupiter, say. It's stealing a little bit of momentum from Jupiter and it's giving it to the Earth, and it's stealing it from Jupiter and giving it to Earth. And slowly the Earth would just move out. But, mathematically, theoretically, it's possible, but practically not with our technology today. But who knows what it'll be like in the future. Whoa, Frosty Winnipeg. Fraser, did you see the For All Mankind Season 4 teaser? I did not. That is awesome. I put For All Mankind in my list of my top 10 space TV shows ever made. So if you've never watched For All Mankind, absolutely watch it. Now, it goes downhill. So like the first one was terrific. Second one was really good. Third season, it was fine. It was pretty good. I hope season 4 is good. But the season 1 and 2 were just terrific. Tim Pointing, how quickly does a star go from having positive energy balance to collapsing and then to a supernova? Yeah, I talked about earlier in this episode that process of going from a massive star to a black hole and giving you a supernova. It happens fast. So the moment in the star it reaches that iron level, like you can be going through the precursors to iron in the days, hours leading up to the death of the star. And then within seconds, like the moment it starts to do the fusing the iron, it no longer has the outward force and it begins to collapse in on itself. And that inward collapse, that implosion happens very fast. That material can be infalling at 70% the speed of light. So it happens in a literal blink of an eye. But stars can be, these stars are big, right? They can be, Betelgeuse is like 800 times more volume than the sun, right? It extends out to the orbit of Jupiter. And so even the light travel time to get out to Jupiter is like an hour, right? So, it's going to take several hours for the thing to actually fully collapse in on itself. And then, and this is the crazy part, is that it takes time for the light to be able to get out of the tangled mass that is the star. The light all piles up inside the star. It has to random walk its way out of the star. And so that's why we see the neutrinos first. The neutrinos are not hampered by the mass of the star. The neutrinos come out, then the light makes its way out of the star, and then the whole star starts to brighten and brighten and brighten and brighten. And that's how you get your supernova. And it, will go through this, it's called the breakout phase. And it takes several hours for the star to go from what it was to the supernova version of itself. It's brightening by factors of thousands. And yet this all happens just in the blink of an eye. Like you can absolutely watch it happen. Kenny Woodward, if we could travel faster than light, would time still slow down? So it all just depends on how we would travel faster than the speed of light. If we use some kind of warp drive where we are changing space-time, but we are not moving through space-time, we're essentially staying still and we are pulling our destination to us, and then we are moving a few millimeters forward, and now we're in that other space-time, and the space-time snaps back, and now we're in our destination, then we've experienced no time dilation. But if we somehow can move through space faster than the speed of light, which violates all the laws of physics as we understand them, then if you punch those numbers into the relativity calculations to say, how much time dilation would you experience negative time. You would arrive at your destination before you left, which doesn't make sense, but that's and so it's like, if you could travel faster than the speed of light through space itself, clearly things would get weird. And, exactly how it would work, we don't know. And probably we'll never find out. Yeah, there you go. Season 5. Yeah, there's a new season coming. Yeah. There's also a new season of Invincible, which is cool, coming up in March. And we're watching the new season of Fallout, which has been terrific. Terry Hardaway, how linked is gravity to electromagnetism? Does the universe have a magnetic field? Is magnetism anti-gravity? Are quasars a result of magnetism? There's a lot of questions there. So how linked is gravity to electromagnetism? It doesn't look like they're linked at all. In fact, this is one of the great challenges in physics, is that gravity explains the sort of the movement of the stars, the movement of the planets, the way masses move around one another, and the other three forces, electromagnetism, the weak force, and the strong force, we know that they were once combined into one force at the very beginning of the universe. And in fact, this can be simulated in particle accelerators like the Large Hadron Collider. So, and you've got quantum mechanics, which does, beautiful, again, predictions about how the universe works at a fundamental microscopic level. And yet there doesn't seem to be any way to unite gravity and electromagnetism, to link them in any way, shape, or form. So we don't know how they connect. And yet this is the thing that Einstein was trying to figure out for the rest of his life. This was his great unsolved mystery. And people have been trying to come up with an answer to this since then. And that's the whole reason why string theory exists, is that it gives a mathematical explanation for how gravity and electromagnetism and the other forces could connect with one another. And there could be some underlying force that is, jiggling strings that are causing these different forces in our universe. Other people consider that to be a wild goose chase. And so we don't know. Does the universe have a magnetic field? In general, the magnetic fields tend to balance out with each other. So I don't know if there's like an overall, there can be a local magnetic field in some region of the universe, but sort of once you go bigger and bigger and bigger, things are going to kind of average themselves out. Is magnetism anti-gravity? No. It is a different force than gravity. And there doesn't seem to be any kind of anti-gravity. Are quasars a result of magnetism? Sort of, yeah. So a quasar is an actively feeding supermassive black hole, where a black hole is feeding on material. There's so much material, kind of like I always sort of describe it as a drain, and you've got too much water going into the drain. And so then the water starts to swirl around the drain. So you get this accretion disk around your black hole. And very powerful magnetic fields happen because all of this material is swirling around. It's plasma. The plasma is charged. You get these magnetic fields. And then the magnetic fields create these jets of material that are coming off of the central black hole and going off into space. Now, the black hole, the rotation of the black hole is powering the system, but you wouldn't get the jets without the magnetism. So are quasars a result of magnetism? They're definitely part of the puzzle, for sure. Frosty Woodpig, channel needs more AI viewers. Don't we have enough AI viewers? Pacer mate, does Europa have life on it? You should check the interview that I did earlier this week. There's reasons why it might not have life on it. Han Solo, do we have any idea why the sun is hotter at its surface than inside? I mean, the corona versus the convective zone of the chromosphere. Right. So the sun is several million degrees Kelvin, 4 million Kelvin at its center. But it's about 6,000 Kelvin on its surface. And yet the atmosphere above the sun can be 1 million Kelvin, the corona. And in like when you see an eclipse, you see these cool wisps of material floating around the sun. That's the corona, the atmosphere of the sun. And this was one of the long-standing questions about the sun. One of the great mysteries is, why is the corona so much hotter than the surface of the sun itself, like 1 million degrees when the surface is 6,000 degrees? And it's only been recently that the answer has finally been revealed. And thanks to the Parker Solar Probe and the Solar Orbiter and the Daniel Kane Solar Telescope and other observatories, that there are these nanoflares that are coming off of the surface of the sun, these jets, and that they are heating up this material that is around sort of the atmosphere of the sun, and it's constant and in heating it up. And so this is an answer that astronomers only recently actually worked out. So, one of the main benefits of sending the Parker Solar Probe was to uncover this. There's some, and this is all still very, very new. There's and like all these like technical terms, alpha waves and such, but yeah, that there are these flares, these constant flares that are coming from the surface of the sun, that are related to the magnetism on the surface of the sun that is heating up the atmosphere around it. Super Luigi Daisy. Fraser, I keep calling you Fraser, and I never seem to escape that. There was a question. I got to read this question out to you because it's so funny. Let me just read it out to you. Here we go. So I won't say who said it, but it says, and who cares? By the way, are you trying to benefit from using a form of Fraser Crane from the sitcoms? If so, you're a jerk. And if not, you're ignorant. So in other words, if I am somehow trying to ride on the coattails of Fraser Crane from Cheers, then I'm a jerk. But if I am like using the name, but not riding the coattails of Kelsey Grammer's groundbreaking work in Cheers, then I am ignorant. Possibility 3, I was born before Cheers, right? I was born in 1971. Cheers is what, 1982? Like I was 11 years old when Cheers came out. And it was several years after Cheers came out that they introduced the character of Frasier. I had the name first. So it's them who should be expecting a call from my legal department for them stealing my name. And anytime, and it was great for a while there when people stopped watching the show and they'd forgotten that Frasier even existed. And then they made a remake and I was like, oh no, this is it. And it flopped. So I think I'm home free at this point. Now I just have to stay alive a few more years and I get to keep, reclaim my name. Mm-hmm. Dean Kovacs, is the microwave background radiation image of the entire universe or just the observable part? The cosmic microwave background radiation, this is this time about 380,000 years after the Big Bang when the universe was finally transparent. So up until that point, the universe was opaque. It was essentially the surface of a star, except everywhere, right? 3,000-ish Kelvin, like the surface of a red giant star. And then around 380,000 years, enough of the universe had started to cool that light could move. It could actually, like the photons weren't just crashing into each other nonstop. They had a little breathing space and they got to move a little ways away from each other. And then over time, the spaces got bigger, the universe got cooler, and more of the universe was transparent. But when you look out into the universe, you are seeing that moment in this sphere around you specifically. And I see a different one. Now, they're very similar because we are living on the same planet, but you are seeing your observable universe. And I don't know how far away you are from me. We could be thousands of kilometers apart. We are seeing two separate overlapping spheres where I can see a little bit more into the universe than you can in one direction. You can see a little more to the universe than I can in the other direction, right? because of our separate observable universes. And yet we are both seeing the cosmic microwave background radiation. And then a year later, we will look out into the universe and we will see the cosmic microwave background radiation, because it is a new spot, a place that is 1 light year farther, where the light was able to escape because now it had become transparent. The photons have been traveling for 13.8 billion years to reach our eyeballs. And then 1 year later, it's the observable universe has grown. It's a bit of a bigger sphere around us now. And now new light photons that have been traveling for all this time finally make it to our eyes. And so, and like this is the thing that when you kind of finally get it, you'd be like, whoa, which is that when we think about the cosmic, because we can't see it, right? We don't have microwaves for eyes, but if we could, we are seeing that birth shout of visible light in the universe for the first time, always. And it's this constant first shout continuously. And it will be so throughout the future, that a person 10 billion years from now will look out into the universe, will see the cosmic microwave background radiation, and it will be the first light that was making its way through the universe had finally reached them. J. Cello 2B. We keep looking for life in the universe. Maybe we should focus on just making life that can survive in space. Should we embrace the opportunity? Well, why choose? Why can't we both walk and chew gum? They are two separate things. One is observing the universe to find out if there's life out there. And that is a very important question and could have real implications for our existence down here on Earth. Like, imagine if we received a transmission from an alien civilization, or we saw evidence of an alien civilization having a nuclear war, or we could detect the presence of gases in their atmospheres, or we find some kind of ancient robotic factory here in the solar system. That would be interesting, and then we could study the technology and learn about it. So we want to search for evidence of life, and then maybe we should focus on just making life that can survive in space. Like, that's a thing that we're going to be doing as well. We are transitioning into a solar system spanning civilization. We are building rockets capable of taking us to the stars. We have robots that are crawling around on other worlds right now. We are getting better and better at mastering the challenges of living and working and exploring space. And they are mutually exclusive. They have nothing to do with each other. Unless we find the alien factory in the asteroid belt and we need to build a mission to be able to go there, then yeah, the technology of us being able to fly in space will teach us about space. But like, I never understand when people have this, you should just do this one thing. Like, we do all kinds of things, right? You should only watch one television show ever, right? Don't play video games. You are only meant to watch television shows or YouTube videos. In fact, you're only meant to watch my channel. Do not watch any other channels, and really don't participate in any other media at all, or even talk to other people. All you should be doing is watching Fraser's videos. No, we do all kinds of things. And we do that as a, some people, we're not just one person. We contain multitudes. And some of us want to search for aliens, and some of us want to go and live in space. And money can be spent on both. And instead of the money that gets spent on military equipment or lawn care. Where are we at? Okay. GT Zivalis. Theoretically, how far would I have to travel to find a perfect copy of myself, Earth, the solar system, the Milky Way? I think some of the numbers are 10 to the power of 10 to the power of 200 meters. I don't know the exact numbers for those. And I don't know if we can know. But, this is this idea that if you have a finite sort of number of combinations, that configurations that the universe can be in, if you take a cubic meter of space, there's like whatever 10 to the power of 80 different configurations of particles that can go within that cubic meter of space. And that if the universe is bigger than 10 to the power of 80 cubic meters of space, then you're going to have a repeat, right? So you'll have every combination, and then you'll have two that are identical. And if space is infinite, then these things will repeat. And I don't know what the number is. Like, it is big. Maybe Sean Carroll has done the math in his podcast, but I don't know what the number is. But it is big. Sean Carroll did a paper looking at how long it would take for there to be another Big Bang. And that was in that sort of like 10 to the power of 10 to the power of 80. I forget the exact number. It was a 10 to the power of 1,000, some gigantic number that would take a very long time, but you would theoretically get another Big Bang at the end of that. Arjun, when they say the background temperature of the universe is currently X degrees, what are they measuring? Is the temperature of a certain size area? Are supervoids already near absolute zero? They're measuring the temperature of the photons that are coming from the cosmic microwave background radiation. It's 2.7 Kelvin. And it has minute fluctuations. So it can be like 2.7001, 2.699999, right? Like, it'd be really close and a little bit higher and a little bit lower than 2.7, but on average it's about 2.7 Kelvin. So they're just measuring the temperature in the same way that you would measure the temperature of sunlight, measure the temperature of infrared radiation, so you're measuring the wavelength that's coming from the microwaves. Is it a temperature of a certain size area? It's everywhere. Like, every photon that's coming from the cosmic microwave background radiation is roughly that temperature, that black body radiation. The cosmic microwave background radiation is like the most perfect black body radiation never measured. Are supervoids already near absolute zero? No, the supervoids are a little bit warmer than the background radiation temperature of the universe, because it's always warming you up. Like, you can't be absolute zero because the cosmic microwave background radiation is illuminating everything and warming you up. There's like a science fiction story that I read, or maybe it was a paper where someone was talking about how you could live on a black hole and you would experience so much time dilation that the cosmic microwave background would be blue shifted brighter. And so then you would be able to essentially have solar panels that are gathering the light from the cosmic microwave background radiation because you are experiencing so much time dilation. Now, of course, you would be fast forwarding the universe while you're collecting this, but still, you could do this. CF Suzer, Fraser, have you watched Pantheon? Yeah, it's terrific. I really like Pantheon. Very good show. It's animated. It's about the sort of existential horror of intelligent AI. There's 2 seasons, and it has a very similar animation style to Invincible. Deals with some really sort of weighty philosophical topics. There's a bit of kind of gross scariness early on, which, my wife is into horror movies. I'm not, and even she was like, "Oh God, that's gross." So just be prepared for that. But apart from that, it's a great TV show. Visotudi, does Earth still have its birth atmosphere, or is it a reconditioned atmosphere? So we don't know. When the Earth formed, there was going to be a bunch of volatile elements mixed in with the planet's formation. So we have the rock, we have the metal, but we would also have lighter gases, nitrogen, oxygen, things like that. And it's assumed that early on, you got this outgassing from the planet, the radiation from the sun blasted this material away, and so the Earth was relatively dry. And this is why people are always looking for some explanation for how the volatiles were delivered to Earth. How did we get all of the nitrogen, all of the water? Because without the protection of a geomagnetic field, the sun would have blasted away all of that water. It wasn't until the Earth had formed that it began to get plate tectonics. Once it got its dynamo internally, then it could protect its water. And that was while after its formation. And so people are always looking for some kind of mechanism. So some sort of delivery of these volatile elements. So you would also get volcanic outgassing. There's like constantly material that is being belched out from the interior of the Earth that would be thickening the atmosphere. But many of the volatiles were probably delivered later on through comets, through asteroids, things smashing into the planet. So reconditioned is probably the right way to explain it. An atmosphere that was delivered later plus volcanic outgassing. Dougal, have you done any research into which 3D printer would be best for you? I have not. No, I'm leaning towards a resin printer because then I could do like figures for my role-playing games. And then you can paint them. That'd be really cool. But then I was at a bird sanctuary this weekend and they were 3D printing guards that they put over top of the holes for their birdhouses so that raccoons can't stick their arm inside of them. And they're like, oh yeah, like I might want to build things like that. So, and that looked like it was done with an actual filament printer, but probably a resin printer. Johnny Fairlane, any thoughts on neutron stars or their different manifestations? So I don't have any specific thoughts on them, but I just did an interview with somebody about magnetars, and we're probably going to release that interview on Wednesday. And we go into what is the formation of magnetars? Where are they coming from? And so it was wondered if, so a new theory is that, okay, I need to put a bunch more information here. Okay, so magnetars are a type of neutron star, which is what you get when a massive star dies as a supernova, collapses in on itself. You end up with this piece of degenerate matter rotating very rapidly. And when when neutron stars first form, they are rotating like close to 1,000 times a second, 700 times a second. And they're blasting out beams of radio waves, and they're called pulsars. And then they slowly slow down, and then they just become regular old neutron stars. But there is a class of neutron stars called magnetars that have just put out incredibly intense electromagnetic radiation. They are surrounded by these really powerful magnetic fields that would, dismantle your atoms if you got too close, so on. And astronomers kind of don't know why. Like, why do you get these incredibly intense magnetic objects in some situations? What is the cause? And it probably has something to do with a binary star, a binary companion, that maybe you've got a star goes supernova and it has a black hole as a companion, or it has a stellar companion or white dwarf or something. But one theory is that it is the result of a kilonova. So when we think back to 2017, we had this first detection with LIGO of the kilonova, these two stars that, two neutron stars that collided with each other. And then we got this really bright flash. Those are the cause of the short gamma ray bursts. But what did that turn into? What was the result? Did they just vaporize one another? Did they turn into a black hole? One theory is that this is the cause of magnetars. that this is how you get magnetars, is two neutron stars colliding with each other. They don't have enough mass to kick it into a black hole, but they have just enough mass to turn it into a more massive neutron star that is also now spinning incredibly rapidly, surrounded by the material that was sort of gasified as the two neutron stars were colliding with each other. That's how you get a magnetar. And so the researcher that I talked to, they did observations of essentially a kilonova remnant, trying to see if there was any evidence of a magnetar in there as the result of the collision from the neutron star. Spoiler alert, they didn't find it, but it doesn't mean that it isn't there. It doesn't mean that that's not the mechanism. So there you go. You just got the preview of Wednesday's interview. Han Solo, do you know the idea by David Kipping called TARS? Yes. This is the kind of thing that someone would ask me my opinion about, right? Like, Fraser, what's your opinion of Dr. David Kipping's paper on TARS? I don't know. I am a journalist. I can report that Dr. David Kipping has written a paper about his ideas. Check out his paper. He is the doctor. He is the researcher. I am just the journalist. Scout 663, can new forms of life evolve on Earth today? Sure. New forms of life are evolving all the time. Think about bacteria resistance or antibiotic resistance in bacteria, where you've got bacteria, it's doing its thing, it's happy, it's living its life, and then we come up with a poison that kills it. And the bacteria goes, whoa, wait a minute, let me just evolve to handle this. And now the poison doesn't work against the bacteria very well. You're seeing the evolution in real time. But there's plenty of examples of either, some creatures evolving certain traits that make them better equipped in like our lifetimes. Like there's this classic example where there was like a lot of soot in England, I think, back in the 1800s. And so the moths had evolved to look darker. And then when the soot cleared up, the moths evolved to look whiter again because the predators, they wanted to stand out against the rocks that were around them. And so, all the time, evolution is happening constantly across countless creatures here on Earth. Each time they replicate, create a new generation. If they're fitter to be able to handle their environment, you have mutations in your body that are different from either of your parents. And some of those are beneficial. Some of them are harmful. Most of them are nothing. And over time, small changes will add up to an advantage that will then stick from generation to generation. And that is evolution. It's happening all the time. It's just with bacteria, they cycle so quickly that you can force those changes. There was a researcher that I was interviewing a couple of years ago, and he was taking a kind of yeast that was right on the cusp of wanting to turn into a multicellular organism. And he could kind of force it into being a multicellular organism and then bring it back and then put it into multicellular organism and bring it back and just sort of cycle through that. So we see evolution all the time. Salafi 2038. Will any of the upcoming telescopes be able to image nearby exoplanets as a bit more than just a pale dot? Nope. Unfortunately, the biggest telescope that we can build right now today and for the foreseeable future will always show exoplanets as a dot, one pixel. But we will get a lot of information out of that pixel for sure. We have to build a solar gravitational lens where we, use the the gravity of the sun as a natural telescope, or we have to just build a telescope that's bigger than about 100 kilometers across. Like once we get above 100 kilometers across, then we can start to image, multiple pixels on exoplanets. So until then, 1 pixel. Samurai, when's NIAC interview season coming up again? I don't know. Let's see. Did they say? 2026. Key dates. Spring 2026. So the 2025... the 2026 solicitations will be announced mid-March. Okay, here we go, mid-March. So a month and a half. So we should get the phase 1 in mid-March. And I promise you, I will reach out to every single one of them and try to do an interview. Leo Corns, what gas is Jupiter's Great Red Spot composed of, and why is it so red? The Great Red Spot is made of the same stuff as the rest of the surface of Jupiter. Like the upper atmosphere of Jupiter is like a mixture of ammonia, ammonium sulfide, and water vapor, and other chemicals in the atmosphere. Crystals, ammonium crystals, and so why is it red? Well, astronomers aren't entirely sure, but it seems to have something to do with the fact that it is such a big storm that it is pulling material from deeper down under the surface of the atmosphere. Like the atmosphere on Jupiter is only about 70 kilometers deep. So it's, and Jupiter is gigantic, right? And these storms are very much sort of swirling around on the surface of the top of the atmosphere. But the Great Red Spot is so big that it is probably dredging up material from deeper down that has never been hit by sunlight. And so it's like, when you dig up a piece of dirt that's still kind of, or you dig in the dirt and the surface is very kind of dry and then it's like a different color because it's wet, right? It's like that. So it's digging down deep. It's kind of amazing. So like when you go back and watch the original Cosmos, or not the original Cosmos, but the new one with Neil deGrasse Tyson, I think they show some images of like the Voyages or something like that going past the Great Red Spot. And it looks like this sort of depression down, almost like a crater. And then the storm is swirling, but it's backwards, right? Yeah. It's actually a bump above. Sorry. Whatever it was in Cosmos, it's the opposite. I'm trying to remember which way it goes. Anyway, so when you look at Cosmos and you see the Great Red Spot on Jupiter, it's the opposite of what they showed you. Same test channel. Your sound signal is weak, perhaps your mic gain or an OBS. Yeah, it's probably an OBS, but I have got it cranked in OBS. Like you just have to turn your volume up. Because the volume gain in OBS is perfect. Like it's going up into the yellow, but it's not peaking up into the red. So I don't want to increase the gain in OBS any louder, but I can have am I using a filter? Yeah. So I've got a 10 decibel filter on my microphone that is making it even louder as well. And the thing that's most important is that we have good audio that then my editors can turn into the podcast and stuff that we do. So just turn the volume up if you need to. But I'm guessing you're technically knowledgeable and know that, that there's a certain loudness that these mics have. But we're tuning it for what sounds good when we mix it into our episodes. Blackberry. Why aren't we sending out probes to those interesting, relatively close exoplanets now? Is it more a matter of incentive or technological limitations? It is absolutely a technological limitation that if we want to send a probe out to one of those relatively close exoplanets right now, let's take the closest one. We know that there are planets around the closest star to the sun, Proxima Centauri, 4.26 light years away. It would take us about 10,000 years for us to send a spacecraft at our best speed to be able to get to Proxima Centauri. I don't know about you, but that feels like it's a little long to wait. And so I'm sure you're saying, well, why don't they just go faster? And to that, I will say, how? We don't know how. We do not know how to go faster than to take 10,000 years to get to Proxima Centauri. Now, there are ideas, right? There are plans, concepts. You could use laser sails. You could use light sails. You could use mag sails. You could use fusion drives. You could use fission drives, all this kind of stuff. There's all these ideas. You know, a series of slingshots. Still, we don't know how to do this. You know, this was the whole idea of the Breakthrough Starshot Foundation, that they were going to give $100 million to various researchers to maybe be able to make a spaceship that would be able to get to another exoplanet at 10% the speed of light, that it would take you 40 years, 50 years to get to Proxima Centauri. And that fell through. And so we are decades, if not hundreds of years away from having the technology for us to be able to send a spacecraft to the very closest exoplanets that we know of. Not to mention, you know, all those other ones that are out there that are 10 light years away, 100 light years away, 1,000 light years away. Zeldaborg Galactic Defender. Follow-up to my SETI TRAPPIST-1 question. I've heard you say that we could detect ourselves within 100 light years. Is that true? Would we know definitively, or are we just detecting oxygen and gas? So that detection that I mentioned, there's actually a bunch. Like, it's a more nuanced answer than just we would be able to detect ourselves at 100 light years away. So there are certain things that we do, like the composition of our atmosphere, the city lights that we have, the various nuclear tests that have gone off, that you would only be able to detect within, say, the Oort cloud of the solar system. That really, you'd have to be inside the solar system to detect that presence. The 100 light years number that I will often talk about, that is that when the square kilometer array comes online, which is this huge radio telescope that's being built in Australia and South Africa, when that comes online, it would be capable of detecting Earth's radio air traffic control system from 100 light years away. That the sort of the magnitude of the radiation coming from our air traffic control system is so bright that it would be detectable at 100 light years away with the square kilometer array. But that's not the brightest thing that humanity has ever done. I don't mean that as the smartest thing, but that is not the most luminous thing that humanity has ever done. So there's, back when Arecibo was a functional telescope and not a crumpled pile of metal in Puerto Rico, it had the planetary radar system. So it would use the dish to focus and concentrate this pulse of radio waves out into space. And then that would bounce off of an asteroid, and then it would come back, and then they would be able to analyze the shape of the asteroid. And it's incredible. Like, you can map out the surfaces of these asteroids as they're passing nearby to the Earth because of this radar pulse that is done from Arecibo. But if you were on the other side of that radar pulse when it went off, it was so bright that you could see it about 25,000 light years away. Now, it didn't happen very often, and it happened in a very specific location in the sky, but it was so bright that it would be super obvious to us with our current technology, if we had radio telescopes pointed in the sky, looking at the spot, and a radar pulse of that magnitude happened to be pointed at us, you know, that star system could be 25,000 light years away and we would detect it. So that is the brightest thing humanity has ever released into space. And unfortunately, Arecibo is now offline, obviously. There are some other radar systems that are used for astronomy, but they're not as powerful as Arecibo was. And so for a while, we will not be creating such a loud scream, a radio scream into the cosmos. All right. We've reached the end of our episode. So thank you for hanging out with me. Thanks in advance to Chad and Anton, who are going to have to edit all this nonsense together. Thanks to the moderators. Thanks to Zapfan for grabbing those questions and putting them into the database. I couldn't do this without you. I mean, I could do this poorly without you. I mean, no pressure, man. But, you know, thank you. What's coming up? So, question show tomorrow. Interview Wednesday, question show Thursday, and a new Space Bites on Friday. And so this episode is going to not be made unlisted. This episode is going to remain sitting here on our YouTube channel, publicly available. So we need some kind of secret code to say that you made it all the way to the end of the episode. Anton will think of a clever way to think about this, but we will have some way to know. Did you watch all the way to the end of this episode? Thank you. And we'll see you all next week. Oh, and next week is going to be Australia time. So it'll be late Sunday night for me, and it'll be early morning Europe and super late for the East Coast of North America, but afternoon, evening for people in Asia. All right. Thanks, everyone. And we will see you next week. Where's the button?